Welcome again. In this session, we are going to discuss about the polynomial equations involving complex numbers. So we begin by explaining the simple solution of a quadratic equation whose roots are complex numbers. So given a quadratic equation, az squared plus bz plus c equals to 0, then the solution or the roots are given by z equals to minus b plus or minus square root of b squared minus 4ac divided by 2a. This is by quadratic formula. So b squared minus 4ac, if this quantity is negative, then we have two complex conjugate solutions. So let alpha and beta be the two roots. Let me call this equation star. Be the two roots of star. Then z minus alpha times z minus beta should give us 1. Should give us 0. So when we multiply this, this would give us 0. So this will have z squared minus beta z minus alpha z minus alpha times minus beta will give us plus alpha beta equals to 0. So this can be rearranged as z squared minus alpha plus beta z plus alpha beta equals to 0. And if you are to compare with the equation equation star, so star can be written as z squared plus b over az plus c over a equals to 0. This is simply obtained by dividing each of these terms in star by coefficient of z squared a. So if I call this 1 and I call this new of star 2, then from 1 and 2, we can clearly see that alpha plus beta is the same as negative b over a, while alpha times beta is the same as c over a. And this relationship between the coefficients of a quadratic equation and its roots is usually called the Wiertz relations or identities. So these are called the Wiertz relations or Wiertz identities. So it relates the coefficients of a quadratic or a polynomial equation to the roots of the polynomial equation. So let's give an example. Given alpha is 7 plus 2i is one of the roots of a quadratic equation with the real coefficients, A, state the value of the other root, beta, and then B, find the quadratic equation, and then C, find the value of alpha plus beta and alpha times beta, and then interpret the result. So this is a very nice problem. And for us to respond to this problem, we recall that when you have a quadratic equation, whose roots are complex numbers, as we have been given in this question that one of the roots is 7 plus 2i, then the other root, which is given by beta, is simply the conjugate of the root that is given. So part A, beta is nothing but conjugate of this complex number is 7 minus 2i. Then since alpha equals to 7 plus 2i and beta equals to 7 minus 2i, then the quadratic equation is simply z minus alpha multiplied by z minus beta equals to 0. So we can have this as z squared minus beta z minus alpha z plus alpha beta equals to 0. So which we can write this one as z squared minus alpha plus beta z plus alpha beta equals to 0. Then we just put in the values of alpha and beta. So we'll have z squared minus 7 plus 2i plus 7 minus 2i, z plus 7 plus 2i, then 7 minus 2i equals to 0. So this will give us z squared minus 7 plus 7. This will give us 0, so this will be 14. Z plus 7 times 7 is 49. 7 times minus 2i is minus 14i. 2i times 7 is plus 14i. Plus times minus is minus, but I times I is I squared, whose value is minus 1. So to give us plus 4 equals to 0. So we'll have z squared minus 14z. Now minus 14i plus 14i cancels out. 49 plus 4 is 53. And this will be our quadratic equation. Then find the values of alpha plus beta and alpha times beta, then interpret the results. Part C, alpha plus beta is 7 plus 2i plus 7 minus 2i, whose value is 14. And then alpha times beta is 7 plus 2i times 7 minus 2i. 7 by 7 is 49. 7 by minus 2i is minus 14i. 2i times 7 is plus 14i. Plus times minus is minus, but I squared is minus 1, so we'll have plus 4. And this will give us 53. So we realize that the values of alpha plus beta, which is 14, and alpha beta equals to 53. These are simply the coefficients. So the negative alpha plus beta, which is 14 minus 14, is a coefficient of z, and alpha beta, which is 53, is a constant term in the quadratic equation. In part B given. So just simply it's an argument with the Weiss relation between the sum and product of the roots of the equation and the equation itself. So another example, example 2, given that minus 1 is a root of the equation z cubed minus z squared plus 3z plus k equals to 0. Part A, find the value of k. And then part B, find the other two roots. So remember, when you are told that z, the negative one is a root of the equation, it means that when you replace where there's variable z by minus 1 into the equation must be satisfied. So part A of the equation is as good as replace z for minus 1 and solve for k. So z equals to minus 1 will give minus 1 power 3 minus minus 1 squared plus 3 times minus 1, then plus k equals to 0. So this will give us negative 1 plus 1 minus 3 plus k equals to 0. So minus 1 plus 1 is 0. So minus 3 plus k equals to 0. And we get k equals to 3 as the solution for, okay, so this is 3 times minus 1. So this minus 3. And then 3 minus 1 cubed. That's minus 1. So this is a minus, so sorry for that. This part, this sign is minus. Because the square of minus 1 is just positive 1, but you have a minus sign here. So minus 1 minus 1 minus, so this will be minus 5. So k will be positive 5. So with the K5, then we'll have part B. The quadratic equation will be, the polynomial equation will be z power 3 minus z squared plus 3z plus 5 equals to 0. Now, since z equals to minus 1 is a root, then when you take minus 1 to this side, it will be plus. So z plus 1 is a factor of this polynomial on the left-hand side, z cubed minus z squared plus 3z plus 5. These are actually basic properties of polynomials. So once you have z equals to minus 1 being one of the roots, then z plus 1 must be a factor of the polynomial on the left-hand side. So this by factor theorem, work of college algebra. So we can now do long division to see how many times does z plus 1 divide this cubic polynomial. So we need to find what to multiply by z to get z power 3, and that is z squared. So z squared times z is z power 3. Z squared times 1 is positive z squared. Then we subtract in the so z cubed minus z cubed is 0, minus z squared is minus 2z squared. Then bring these other two terms, 3z plus 5. Then we need to multiply minus 2 by z to get minus 2z squared. So I'll have minus 2z. So I'll have minus 2z squared. Minus 2z times 1 is minus 2z. Then we subtract in the usual way. So I'll have minus z squared minus 2z squared minus 2z squared is 0. 3z minus 2z is 5z, then plus 5. So I need to multiply this by 5 to get 5z. And then 5 times 1 is 5. So when I subtract here, I get 0. So therefore, z cubed minus z squared plus 3z plus 5 is the same as z plus 1 multiplied by this quotient, z squared minus 2z, and then plus 5. And remember, this is always equals to 0 from what you're solving. So this means that z plus 1 equals to 0, or z squared minus 2z plus 5 equals to 0. This we already know that z1 is negative 1. So this other one, we use quadratic formula, which is z will be minus b plus or minus b squared minus 4ac divided by 2a. Our b is minus 2, so we'll have positive 2 plus or minus. Minus 2 squared is 4, minus 4 times 1 times 5 divided by 2 times 1. So z will be 2 plus or minus square root of 4 minus 20 is minus 16 divided by 2. So this is 2 plus or minus 4i divided by 2. So which will give us z equals to 1 plus or minus 2i. So this we can say z2 is 1 plus 2i, and z3 is 1 minus 2i. So therefore, the roots of the other two roots of the cubic equation given is 1 plus 2i and minus 1 minus 2i as the other root. Example 3, given that 3 plus I is a root of the quadratic equation. So quadratic means highest power is 4. 2z power 4 minus 3z cubed minus 39z squared plus 120z minus 50 equals to 0. Solve the equation completely. Solve the equation completely. So I've been given one of the roots of the quadratic equation, 2z power 4 minus 3z cubed minus 39z squared plus 120z minus 50 equals to 0. So we have to solve the equation completely. So recall that if one of the solution of the polynomial equation is a complex number, then the conjugate of that complex number is also another root of the same equation. So we begin by saying solution, since z equals to 3 plus I is a root, then conjugate of this, which is 3 minus I, is another root. That must always be. So then z minus 3 plus I, when you multiply by z minus 3 plus minus the conjugate of this other root, is a factor of the given quadratic equation. So this is what you're saying, that in general, if you have one complex root of a polynomial equation, then the conjugate of that complex root is another root of the same equation. So which means that also when you multiply the two, when you form a quadratic equation using the complex root and its conjugate must always be a factor of the same polynomial equation. It's true in general, provided that the roots are provided that you are dealing with the polynomial equation involving quadratic roots, involving complex roots. So this will be the same as z squared minus 3 minus I z, then minus 3 plus I z, minus minus is plus, 3 plus I times 3 minus I. So this is the same as z cubed minus 3z minus or plus I z minus 3z minus I z plus 3 times 3 is 9, 3 times minus I is minus 3I, I times 3 is plus 3I, plus minus is minus, but I squared is minus, so it'll be plus. So which means then that this and this cancels out, this and this cancels out. So remember, this is square, not cube. So z square minus 3 minus 3 is minus 6z, and then plus 9 plus 1 is 10. So z squared minus 6z plus 10 is a factor of the given quadratic equation. So therefore, we do long division. z squared minus 6z plus 10. We divide with what was given on the left-hand side for the quadratic equation, 2z power 4 minus 3z power 3 minus 39z squared, and then plus 120z, and then minus 50. So I need to multiply this by z power 2 to 2z power 2 to get 2z power 4. So I'll have 2z power 4. 2 times minus 6 is minus 12. Then z power 3. 2 times 10 is 20. Z squared. Then I subtract. So this will be minus 3 minus 12. I'll get 9z power 3. Minus 39 minus 20 will give me minus 59z squared, then plus 120z minus 50. Then I need to multiply this by 9z, so that I get 9z power 3. So this will be 9z power 3. 9 times minus 6 is minus 54z squared. 9 times 10 is 90z. And then I subtract. So 9z power 3 minus 9z power 3 is 0. Minus 59 minus 54 will be minus 59 plus 54, which is minus 5z squared. And then 120 minus 90 is positive 30z, then minus 50. Then I need to multiply z squared by minus 5 to get minus 5z squared. So this will give me minus 5z squared. Minus 5 times minus 6 is positive 30. Minus 5 times minus 10 is minus 50. Then when I subtract, I get 0. So therefore, z 2z power 4 minus 3z power 3 minus 39z squared plus 120z minus 50 is the same as z squared minus 6z plus 10 multiplied by the quotient here. We have found the answer to be 2z squared, then plus 9z minus 5 equals to 0. So that is what is the right-hand side of the equation. So this means that we'll have z squared minus 6z plus 10 equals to 0, or we have 2z squared plus 9z minus 5 equals to 0. The beauty is that the roots of the first one, we already know that z1 is the same as what was already given is 3 plus I. And then z2 is the same as 3 minus I. So just solve this one, then get the 4 roots. So using quadratic formula, we'll have minus b plus or minus b squared minus 4ac over 2a. So I'll have minus 9 plus or minus 9 squared is 81. 4 times 2 times minus 5 divided by 2 times 2. So I'll have z is minus 9 plus or minus 81 plus. So 4 times 5 is 20 times 2 is 40 divided by 4. So this is minus 9 plus or minus square root of 81 plus 40 will give me 121 over 4. So z will be minus 9 plus or minus 121 is square root of 121 is 11 over 4. So z3 would be minus 9 plus 11 over 4. Then z4 will be minus 9 minus 11 over 4. So minus 9 plus 11 is 2 over 4, which will be a half. And then this will be minus 20 over 4, which is minus 5. So therefore, the roots of the given quadratic equation are z1 equals to 3 plus I, z2 equals to 3 minus I, z3 equals to a half, and z4 equals to minus 5. So those are the roots of that given equation. So lastly, show that z power 4 plus z power 2 plus 4 is a factor of z power 4 minus 2z power 3 plus 21z squared minus 8z plus 68. Hence solve the equation z power 4 minus 2z power 3 plus 21z power 2 minus 8z plus 68 equals to 0. So here's just to show that when we divide z squared plus 4 by this given quadratic polynomial, then the remainder is 0. So using long division, we have z power 2 plus 4. Then this is z power 4 minus 2z power 3 plus 21z power 2 minus 8z plus 68. So z squared, you need to multiply by z squared to get z power 4. And then this will be plus 4z power 3, z power 2. Then you subtract. So we'll have minus 2z power 3, 21z squared minus 4z squared will give us plus 17z squared, and then minus 8z, then plus 68. Then you need to multiply this by minus 2z to get minus 2z power 3, then minus 8z, and then you subtract, you'll have 17z squared minus 8z minus 8z will give us 0, and then plus 68. Then I need to multiply 17 by z squared to get 17z squared. So I'll have 17z squared. 17 times 4 is 68. And when I subtract, I get 0. So therefore, there is the remainder is 0. Hence, z power 4 plus power 2 plus 4 is a factor of z power 4 minus 2z power 3 plus 21z squared, and then minus 8z plus 68. So part B, z power 4 minus 2z power 3 plus 21z squared minus 8z plus 68 can be written as z squared plus 4 times this quotient, which is z squared, and then minus 2z, then plus 17. And so solving this is the same thing as writing z squared plus 4 into z squared minus 2z plus 17 equals to 0. And so z squared plus 4 equals to 0, or z squared minus 2z plus 17 equals to 0. So this one means z squared is the same as minus 4, so which means z is plus or minus 2i. And then you can use quadratic formula to solve this to get z equals to 1 plus or minus 4i. And those will be the roots of the given equation in part B. So therefore, z1 equals to 2i, z2 equals to minus 2i, z3 equals to 1 plus 4i, and z4 equals to 1 minus 4i. Thank you.